All right, so now that we've gone over just some of the basics of polar coordinates and polar graphs, we're going to go ahead and move on to the actual calculus portion. So we're going to look at polar derivatives. So polar derivatives would be can be defined two different ways. So one is dr d theta, and what that means is it's the rate that the radius is changing with respect to the angle. So that's why it has an r and a theta. It gives you information about the points that are farthest away from the origin. Which makes sense if you think about it because the radius is changing. It tells whether the radius is decreasing, less than 0, or increasing, greater than 0. And it's just a regular derivative. All right, dy dx is the rate that x is changing with respect to y. It tells you the slope of the tangent line. So that's kind of normal, that's what we're used to. And since when we are given equations in polar form, we are given r of theta, we can change this to parametric and then find dy dx, all right? So to change it to a parametric, we're going to recall from the notes that we did, just reviewing polar, that the x portion would be r cos theta and the y portion would be r sine theta. And so that's how we convert it to parametric, and then we'll go ahead and find the derivative from there. Now, since we have r times cos, that's the product, and so when we go ahead and find this, we're always going to be using the product rule. So the formula for dy dx is just like parametric. We have the derivative of y in terms of theta instead of t, since we're talking about polar, and then the derivative of x in terms of theta. So this is kind of like y prime divided by x prime. Now here, honestly, I never go back and use the formula. I just always do the derivatives by hand for each problem, but I'm going to go ahead and kind of point out to you what this would be. So derivative of y would be first times the derivative of the second, plus the second times the derivative of the first. And then we would have the first times the derivative of the second, plus the second times the derivative of the first. All right? And so typically, since we're given an equation r in terms of theta, this would not literally be an r. This would be an equation itself that you'd be plugging into r. So this r prime really is whatever the derivative of that equation is. Okay, so you can use the formula if you want. You'd have to memorize it, or else you can kind of just treat it the way we did when we learned about parametric and just do y prime divided by x prime. All right, so just a little note, r is differentiable at r theta, where dx d theta does not equal 0, so that's just saying it can't be undefined at the point r theta. All right, so horizontal tangent lines happen when the slope is 0, we know that. And so that means that the numerator is 0, which means that dy d theta equals 0 when you have a horizontal tangent line. And this only works when dx d theta is not 0. So the slope is 0 when the top equals 0 only, you can't have the bottom equal 0. Vertical tangent lines happen when the slope is undefined, which means that the denominator equals 0, because that's how we have undefined fractions when you're dividing by 0 on the bottom. That's where dx d theta equals 0 and dy d theta cannot equal 0. Okay, so in this case, we're specifying you can only have 0 in one of the pieces of the fraction, not both. If you ever have a fraction where it's 0 on the top and the bottom, then you have no conclusion. It means that there's a sharp corner there. Okay, so no vertical tangent, no horizontal tangent, just nothing. All right. So we're going to go ahead and do some examples now using just kind of these formulas, basically. So the first is just straight up, we're going to go ahead and find dy dx. So before I do that, I have to think about converting this into a parametric equation, and the way that I do that is I recall that the x, or the horizontal component, is going to be r times cos theta, And so we have x equals r times cos theta. So that was my equation for r, and I'm doing r times cos theta. So I get x is 2 cos theta plus cos squared theta. Y is going to be r sine theta. So y equals r times sine theta, which gives me 2 sine theta plus cos theta sine theta. Okay. So you could have not written this part out or this part and used just these two and gone back and used the formula, but like I said, I don't really use that formula. I just go ahead and do the derivatives by hand. So the derivative of y is the derivative of 2 sine, which is 2 times cos, and then here we have a product rule. So first times the derivative of the second plus the second times the derivative of the first. So there's my y prime. My x prime, the derivative of 2 cos would be negative 2 sine. With this part, I have to think of cos squared as cos theta in parentheses with the squared on the outside, so I know that that's a chain rule. So that would give me 2, there's my cos on the inside, and my exponent has dropped by 1. And then the derivative of the inside is negative sine theta. So I can go ahead and just kind of clean this up a bit. I have 2 cos theta plus cos squared theta minus sine squared theta, negative 2 sine theta minus 2 cos theta sine theta. And there's so many coses and sines it feels like you should be able to simplify that, but you really can't. That's just kind of it. I guess you could take out a GCF on the top and bottom, but they don't end up canceling because the GCF on the bottom is sine, or negative 2 sine. The GCF on the top is cos. You could pull it out and call it a cotangent, but I don't feel like that actually helps. Okay, so this is a fine answer right there for your derivative. All right, so example 2 says find the points where the horizontal and vertical tangent lines occur, given that r equals sine theta. Okay, so we're just going to recall that horizontal tangents are when dy d theta equals 0, and vertical tangents are where dx d theta equals 0. So if you want to go ahead and like write out the dy dx so that you can just remember this whole top is 0, bottom is 0, I think that that is usually good just because it helps you not have abstract memorizing of formulas, and it keeps it more common sense. So that's what I'm going to go ahead and do. But if you want to shortcut that, that's fine. So again, for parametric, x equals r cos theta, which means we're going to have x equals r cos theta, and that one doesn't really need any simplifying. Y equals r sine theta, and so y equals sine theta, there's my r, times sine theta. I'll go ahead and simplify that. Okay, so my dy dx is going to be y prime divided by x prime. So for y, I have that chain rule. I have to think about sine theta in parentheses with the squared on the outside. And so that gives me 2 times sine theta to the 1. And then if I multiply by the inside, the derivative of the inside, I get cos. For the derivative of x, I have the first times the derivative of the second plus the second times the derivative of the first. So I'm going to go ahead and just simplify that. I should maybe be conserving space. Oh well. I have 2 sine theta cos theta, and then negative sine squared plus cos squared. Okay, so for me to check to see where the horizontal tangents are, I'm going to say 2 sine theta cos theta equals 0. So here's my horizontal tangents. For my vertical tangents, I'm going to say negative sine squared theta equals cos squared theta. Okay, so I'm going to think of this like a factoring problem, almost like if you had a problem where you said x minus 1 in parentheses, x minus 2 in parentheses, then you would have set both of those equal to 0, and then you'd solve and be like, oh, x equals 1, x equals 2. So what we're going to do is we're going to think of this as like 2 times sine of something times cos of something, and basically we can set these as separate factors equal to 0 and solve them. So I'm going to say sine theta equals 0 and cos theta equals 0. So, and they said that it was 0 to pi. So I'm picturing the unit circle where the sine value equals 0, and that happens in 2 places. It happens at 0 and at pi. And technically I would say 2 pi as well, except it's not on the interval they gave me for the problem. Cos equals 0 at pi halves and 3 pi halves, but I should not write down 3 pi halves because it's not in the interval. Okay, so I'm going to leave that there for a second. I'm going to go ahead and solve this one. I wrote it wrong. Plus. Okay. So that was me taking the bottom and setting it equal to 0. So to solve this equation, please do not square root that whole thing. That's not a math property. You can't do that. So I'm going to add the sine squared to the other side. I guess another option would be you could get out your sheet with your trig identities and convert one of these in terms of the other. That would work as well. But it kind of works to do it this way. Whatever your preference is fine. So I get plus or minus cos theta equals plus or minus sine theta. I'm trying to think of... Sorry for that awkward pause. What I did is I was trying to think about if I would have to have this be positive while that's positive, or if it was all the combinations. So I did it the other way on a separate sheet of paper to make sure I was doing it correctly. Okay, so if we think about this, what this means is that we were looking on the unit circle for where the value of cos and the value of sine are the same number, and it doesn't matter what the signs are, because we could have this be positive while this is positive, or this one be positive while that one's negative, all the different combinations. So we know that sine and cos are the same number with the root 2 over 2. And so we're basically taking all the points where there's a root 2 over 2. And so on the unit circle, that means we're looking at pi fourths and 3 pi fourths. We would be looking at 5 pi fourths and 7 pi fourths. Except that those are not between 0 and pi. And so that means that these are the answers we have. So right now, what we're going to do is we're going to look at all of these together. And the reason we look at all of these together is because we want to make sure that none of these are duplicates, because if they are, that means there's a sharp corner there. So based off this, we can see there's no duplicates, so there's no sharp corners. All right, so now I can go through and I can find the points. So I have, this is going to be r theta. So I'm going to say r equals sine of 0, which is 0. So that gives me the point 0, 0. R equals sine of pi, which gives me 0. So that's the point 0 pi. R equals sine of pi halves, which is 1, so that gives me the point 1 pi halves. Okay, so in each of these I was plugging in to that equation they gave me in the beginning, r equals sine of theta. Okay, and then over here, so there's my horizontal tangent lines are happening at those points. For my vertical tangent lines, they're going to be happening where r equals sine of pi fourths, which is root 2 over 2 for the radius and pi fourths for the angle. And then r equals sine of 3 pi fourths, which is again a radius of root 2 over 2, and then 3 pi fourths for the angle. All right. All right, I'm gonna save example 3 to do in class because it's like example 2, but there's a lot more work involved in solving, so I'm gonna explain that in person. We're gonna go ahead and look at example 4. So it says find the tangent lines at the pole. And if you guys remember, the pole is the same thing as the origin, so this is the point 0, 0, but this means specifically that the r value is 0. And they're giving us this polar equation on 0 pi. So I'm going to go ahead and take r and set it equal to 0, so that means that I have 0 equals 2 cos of 3 theta. And so I'm going to go ahead and go through the process to solve for theta so that I know where those tangent lines are. So I'm going to go ahead and divide by 2, which gives me 2 equals cos of 3 theta. And so I'm looking at the unit circle to see where is cos 0, where there's an x-coordinate of 0, and that happens in 2 spots, which is pi halves and 3 pi halves. So what I'm going to say is that 3 theta equals pi halves, and 3 theta equals 5 pi. Not 5, 3 pi halves. Okay. Now, one thing we do to make sure that we can get all the answers is we want to think about not just pi halves and 3 pi halves, but where the coterminal values are for those. So I'm going to say plus 2 pi k and plus 2 pi k, because that's going to give me all of the answers. So if I add 2 pi, then that would be 5 pi halves. That would be 7 pi halves. It'd give me all the different ones. And then I'm going to go ahead and divide by 3, and divide by 3, and divide by 3. And so that means that theta is pi over 6 plus 2 pi thirds k. So it's telling me what other answers to consider. For this one, I'm going to divide by 3, divide by 3, divide by 3. This would be 3 pi over 6, which is pi halves. Okay, so the theta values that we need to consider would be pi 6, and then if I add 2/3 to that, that's like adding 4 over 6. Adding 4 over 6 would be 5, 6. And then I don't want any values bigger than that because I'm only looking at values that are from 0 to pi. And then here I'm going to say pi halves. Pi halves plus 2 pi thirds would be bigger than pi, and so that's all we're considering. Okay, so this, and if we need to talk about this in class, we can. This is kind of going back to pre-calculus about solving trig equations. Okay, so the tangent lines at the pole are happening specifically at these 3 values, okay? All right, now we need to think back to how our derivatives work. So we are doing, we have tangent lines at the pole. We're thinking back to those notes on the first page. If the derivative is less than 0, then the radius is decreasing. If the derivative is greater than 0, then the radius is increasing. If the derivative were to equal 0 exactly, then nothing would be happening there. And so what we need to do is we need to go back and we need to make sure that r prime of theta does not equal 0 at any of these points, okay? So we're going to say, I'm going to write a note up here. We'll have tangent lines wherever r equals 0, as long as r prime of theta does not equal 0. Okay, so what we're going to do is we're going to check all three of these points. So r prime of theta is derivative of the outside, so that's negative 2 sine of 3 theta multiplied by the derivative of the inside, which is just 3. So that's negative 6 sine 3 theta. Okay, so now we're going to check each of the points. So we have negative 6 sine 3 times pi over 6. So that's negative 6 sine of pi halves, and sine of pi halves is 1. So that doesn't equal 0, that equals negative 6. Negative 6 sine 3 times 5 pi over 6. That would be 5 halves, which is coterminal to 1 half, so again, that doesn't equal 0. Negative 6 sine 3 times pi halves. Sine of 3 pi halves is negative 1, so negative 1 times negative 6 is positive 6, so that does not equal 0. So that means that all three of these answers are good. So that's just one little thing we have to check for on these, is we have to make sure that whatever values we have, the derivative does not equal 0.